In this video, we are going to talk about ozonolysis of alkynes and alkenes. For example, if we have this organic molecule and then we put in ozone in dimethyl sulfide, what we are going to do is that we are going to cleave this bond into two to give aldehydes and alkanones. So if here was to be a methyl group, and you see that if R was to be a methyl group and H was to be a methyl group, then you see that in this place we will produce an alkanone or a ketone. And then if this place was to be a methyl group, then we would have produced an aldehyde in this situation. On the contrary, if we put an alkyne and then we use ozone in water, then we are going to convert this alkyne into carboxylic acids. So we are going to get so this is how the ozonolysis in alkenes and alkynes is. In alkenes, you get alkanones or aldehydes, but in alkynes, you get carboxylic acids. So for example, if we consider this molecule and then we put in ozone in dimethyl sulfide, then this place is going to cleave to give us so you see that this is 2-butene. At the end of the day, we are going to get an ethanol, 2 moles of ethanol. Let's use reaction mechanism to show how this molecule will be converted from this alkene to these moles of ethanol. So our starting material is 2-butene. Now, the structure of ozone is in this form. This one has 2 lone pairs, and then this one has 6 lone pairs. So it has a negative formal charge. And then this one has a positive formal charge. And then this one has 2 lone pairs. So what will happen is that this center is a nucleophilic center. And then, so it will use this donate lone pairs of electrons to one of the carbons bearing the alkenes. And then the alkene, because there are pi electrons here, it will in turn use this one to also attack this oxygen. And then because there are electron deficiency here, this will cause us to move this bond to that oxygen. So in the next intermediate, this is what we are going to get. So this is the intermediate that we are going to get. However, oxygen-oxygen bonds are weak and very unstable. And therefore, what will happen is that this oxygen-oxygen bond will try to cleave. So this oxygen will use its lone pairs, will donate lone pairs into this carbonyl center. That will cause a cleavage between these 2 carbons. And then the number of electrons here will be excessive, so it will cause this molecule to also cleave and then push the electrons to this oxygen. That will lead us to this intermediate. if you consider this in two intermediates, you see that there is this carbonyl compound here, and then this compound is a carbonyl oxygen. Sorry, a carbonyl oxide. However, you see that this one has a negative formal charge. Nonetheless, because of this double bond and because this oxygen is highly electronegative compared to this carbon, then it will pull these shared pairs of electrons towards itself more than the carbon. So this oxygen has partial negative charge, and then this carbonyl center has a partial positive charge. Now there is a negative formal charge here, and there is a partial negative charge on this oxygen. So it's going to cause a repulsion between these two oxygens. And therefore, in the next step, this molecule would have to turn upside down so that this positive center can be attracted to this negative center. So this is the kind of orientation that these molecules will assume. And because there are partial positive charges here, then it will cause this one to donate its lone pairs to this carbonyl center. And then that would cause this carbonyl center to also donate its lone pairs here. And then it will move this lone pairs to this oxygen. So this is the kind of intermediates that we are going to form. So you see that there's still oxygen-oxygen bonds here, which are unstable. So this oxygen-oxygen bond will cleave. And when they cleave, but remember that this reaction is taking place in the presence of a dimethyl sulfide. And the sulfide has two lone pairs. So it's going to use one of its lone pairs to pick one of this oxygen. It will donate pairs of electrons to this oxygen. That will cause this bond to cleave. And when it causes this bond to cleave, it will also cause this one to cleave. And then shifting the pair of electrons back to this oxygen. So the next intermediate that we are going to get will be this intermediate. So these are the intermediates that we are going to get from the cleavage. Now, if I redraw this well, you see that this molecule, there is a positive formal charge and a negative formal charge. So it's in resonance with this one. So you can move these electrons into this sulfur center to give us a sulfur oxide. And if I redraw these molecules well, you see that this one looks like this. And then this one too, it looks like this. So these are the end product of our reaction. And that is how the mechanism for ozonolysis in alkenes occurs. Now let's come to ozonolysis in alkynes. In the case of alkynes, let's use this starting material. And then this is ozone. I will know that there is a negative formal charge here and a positive formal charge. So just as it happened in alkenes, it will donate one pair of electrons to this carbon triple bond center, and then it will cause this one to move one of its lone pairs to this oxygen. The bonds will be too much, so this oxygen to move its lone pairs to this oxygen bearing a positive formal charge, and that will lead us into this intermediate. But remember that oxygen oxygen bonds are very weak and very unstable. So because of that, this oxygen will move one of its lone pairs to this carbonyl center, and that will cause this one to move one of its lone pairs to this other carbonyl center, causing this bond to cleave. So we are going to get this intermediate. When we consider this intermediate, this is a negative formal charge. And in this carbonyl center, oxygen is more electronegative than this carbon. So it will pull the electrons towards itself, giving it a partial negative charge and here a partial positive charge. So there will be repulsion between this oxygen and oxygen, causing this oxygen to rearrange, causing the molecule to rearrange itself. So this is how the rearrangement is going to be. But remember that there is a partial positive charge here and a partial negative charge here. So this this oxygen is highly nucleophilic, so it will donate pairs of electrons to this carbonyl center, causing it to also donate another pair to this carbonyl center, and that will move this bond to this side, giving us this intermediate. So this is the intermediate we are going to form in solution. But remember that this reaction is happening in the presence of water. And water has two lone pairs. So it will use one of its lone pairs to pick this oxygen. And then that will cause this bond to cleave, causing this one to also cleave. And that will move this pairs of electrons to that oxygen. So the intermediate we are going to form is this molecule. Write the final product of the following reactions. So you see that this is a propyne. When we do ozonolysis in a propyne, in ozonolysis, this side of the carbon-carbon bearing the triple bond will cleave to give us carboxylic acid. So this part will look like this. So we'll get ethanoic acid for this part, and then the other part would look like this. So this is the intermediate we are going to form, a diketone. So let me redraw the diketone. Now this diketone, through rearrangement, will cause this carbonyl centers to cleave, and when it cleaves, it's going to give us the carboxylic acids. And then this one to also be in solution. So this is the mechanism of how ozonolysis happens in alkynes. Then with this one, this part will cleave. If this part cleave, so we are going to get this kind of molecule. So this is what we are going to get, and also another carboxylic acid on this side. But how many carbons are there? 1, 2, 3, 4, 5, 6. So 6 carbons with carboxylic acids at the end. So let's draw the 6 carbons. 1, 2, 3, 4, 5, 6. So we need to draw carboxylic acids at the end of those carbons. So this is the final product that we are going to get. So get the difference. If you do ozonolysis of a straight chain alkyne, you are going to get 2 products. But if you do ozonolysis in a cyclic ring, you are going to get only 1 product. that contains a dioic, a dicarboxylic acid. Or that's the difference. Yeah, what will each of the following give upon ozonolysis? So we have this. This side will cleave. If it cleaves, we are going to get but remember that this is a metal and this side will cleave to give us this. So this is the molecule we are going to get. How many carbons? We have 1, 2, 3, 4, 5, 6, 7, and then 8. So let's draw 8 carbons in a straight chain. 1, 2, 3, 4, 5, 6, 7, 8. And then we have on carbon number 2, so this 1, 2, we have a carbonyl center there. And then on carbon number 7, so 1, 2, 3, 4, 5, 6, 7. We also have another carbonyl center here. So this is the molecule that we are going to form. And in this case, this side will cleave. So if it cleaves, this is what we are going to get. So there's a proton here. And then with this one, there is a carbonyl center over here. So let's count them. 1, 2, 3, 4, 5, 6, and 7. So 7 carbons in a straight chain. 1, 2, 3. 1, 2, 3, 4, 5, 6, and then 7. Then on, so this is the first carbonyl center. So there's an aldehyde. Okay, so let me show it here. So there's an aldehyde here. That's this aldehyde. Then on carbon number 6, there is a ketone. So 1, 2, 3, 4, 5, 6. So there's a ketone here. And this carbon is this one. But on carbon number 5, there is a metal over there. So 1, 2, 3, 4, 5. So there is a metal over here. And that's the molecule you will form. And then let's come to this one. So with this side will also cleave. If it cleaves, this is what we are going to get. So this is the molecule we are going to get. Now let's count the carbons. 1, 2, 3, 4, 5, 6. 6 carbons in a straight chain. So let's draw it. 1, 2, 3, 4, 5, 6. So those are the 6 carbons. And then on carbon number 1, we have an aldehyde. So 1, this carbon is an aldehyde. And then on carbon number 6 too, we have an aldehyde. So we need to also have another aldehyde over here. Then on carbon number 3 and 4, we have methyl groups. So 1, 2, 3. There's a methyl group here. And carbon number 4, there's also another methyl group here. So these are the molecules from that ozonolysis of those molecules.